Great. Lecture 8, volume. So this is the eigenvalue equation for the area. Now I'll show you what happened for the volume and what are the physical consequences which are of weight. Essentially of this little theorem I said that area and volume are a complete basis. So how do we do here? Remember that the volume up to some number, so some power of h bar g is epsilon ijk li lj lk for three lengths emerging from the node, so L1, L2, L3, which is dual to the tetrahedron represented by the volume. So this is the generator of rotation here, this is a generator of rotation here, this is a generator of rotation here, and they act on these indices here. So this can be written explicitly. In fact, the main equation is that the L acting on dj m n of h. This is a generator of a gauge transformation here. Remember how it is defined. This is a limit for a small group element acting here. So when you act with a small group element here, you have a representation matrix. You have just in the limit, you have just the generator of this representation in J. So this is act on the right. So this gives dj m n prime of h, and here you have the generator. Let's call L j n prime n. So it acts on this index here. Okay, in each representation, if you want, the representation matrix can be written as an exponentiation of this thing here in each representation. So there's this object here. Now the point is that L acts on these indices inside here, and the three operator act on the three indices on the same node. Right? So they transform this thing here, acting with three of these matrices on the three on three of these indices, with then an epsilon ijk attached to this sorry, J means two different things here. So this is a vector thing. This is a vector thing, so it's an index. This is extra index which is attached by the I. So the volume as a whole just act on those indices here, which means that the volume as a whole, it's a operator, a linear operator in this finite dimensional Hilbert space, which is J1, Hj1, Hj2, Hj2, Hj3, Hj4. This, I said, has a linear subspace, which is the intertwined space, and since the volume is gauge invariant, it transforms the intertwined space in itself. So this can be done explicitly. You have one of these intertwiners, let's say the K1, it has indices M1, M2, M3, M4. You act with the volume. You have just a matrix acting here, a matrix acting here, a matrix acting here. You have to get a linear combination of similar intertwiners. So you have to get a sum over some V K prime, some numbers, K prime, where these numbers you can compute it explicitly if you know this. It's just boring calculation, but you just look at your reference book in representation of SU2 and everything is explicit. Now it's pretty boring, but these matrices can be computed explicitly, and then to diagonalize them, it means just to diagonalize a matrix, as you do in standard exercises in linear algebra. Of course, these matrices are big when you go into Swinner's spaces with large J, so diagonalization of these matrices is a complicated thing, but can be done, and there are people who have even written little routines software that is on the web that give you the eigenvalue of the volume. You just type the J inside you want, and you get the eigenvalue of the volume. This was a little exercise that people did for a while. There have been efforts to simplify the calculation of this, but I don't know of any simple result. But then, which means that there are let's call the eigenvalue of the volume V. Then there are states V, which are just a linear combination of the states K, Vk. C V K, where there's some coefficients that can be computed through this machinery. And instead of using a basis where you diagonalize, where you have this basis here, you can use this basis there, JL Vn, where you have directly the eigenvalue of the volume. To do it explicitly, it's boring, complicated, and nothing interesting has come out from that. But the point is that obviously these are finite dimensional spaces, so the eigenvalues are discrete. I mean, the eigenvalue for matrices are discrete. So this is a discrete quantum number. This is a discrete quantum number. The area has discrete eigenvalues. The volume has discrete eigenvalue because it's diagonal intertwining space by intertwining space. You're diagonalizing a matrix in a finite dimensional space, so the eigenvalues are discrete. So both volume and area are discrete. What does it mean? First of all, so we cannot have tetrahedra with smaller area, we cannot have tetrahedra with arbitrary small volume, right? You could have, classically, you could have finite area and small volume by squeezing. If I squeeze this point down, the area remains finite, the volume becomes zero. Quantum mechanically, no. There is a sort of either zero or a minimal area and a minimal volume. But there's something more interesting. Let me just keep this states, erase everything else, and come to a major point. One of you before asked about how many degrees of freedom, and the result of the counting was that the geometry of the tetrahedron has 6 degrees of freedom. So there is a 6-parameter family of tetrahedra up to rotations, up to where it is. So two tetrahedra being different if they have a different geometry. They cannot be moved into one another. 6. Okay? But I wrote explicit basis where the quantum numbers depend on the length on the node. So per each tetrahedron, there is one volume quantum number and 4 area quantum number. So in this basis, each tetrahedron has a fixed volume, one number, and fixed area of the faces, 4 numbers, which means 5. What is missing? What's going on? Well, what's going on is something you know very well, which you have seen in quantum mechanics many, many times. The typical example is angular momentum. Take an object, okay, and look at its rotation. Its angular momentum, classically, is 3 variables. The rotation Lx, Ly, and Z. Okay? These become operators in the quantum theory, and you can diagonalize only 2 of them. You can diagonalize only L square and Lz, not 3 of them. So this means that if Lx is fixed, has a value, Ly is spread, and Lz is spread. At maximum, you can diagonalize 2 out of 3 numbers, which means that for a macroscopic object, you can think of angular momentum as a vector. Okay, if I spin this, well, there is a real vector that represents the way it spins, which has 3 components. But if this is small, if this is an electron, this is not really something. An electron is not a little small stone, because it doesn't have a fixed angular momentum. It has an angular momentum in some direction, fixed, sharp, and in other direction, spread. So it's something more complicated. Okay? You cannot measure both together. They cannot be sharp together. Same here. You have 6 variables classically that define the geometry of this object, but you have only 5 variables quantum mechanics that can be sharp together. Of course, there are other states. You can take linear combination of these states when you can choose some other variable and make it sharp and make it this spread, like Lx, Lz, Ly. There are other bases. There's the Lz basis, but then you can write the Lx basis. So you can choose other variables to describe the geometry. Like what? Well, it was erase the GL L prime, LL LL prime. This is an operator that measures this angle here. You can write a basis in which this is sharp, but then some of these are not going to be sharp anymore. Okay, so you can fix the angle of this, but you cannot fix all angles and all. So what you can do? You can fix 4 areas in the volume, or you can fix 4 areas and 1 dihedral angle. And it's pretty obvious that if you fix this dihedral angle, this is also determined, but the other dihedral angle is not. So this dihedral angle and this dihedral angle don't commute with one another. It's like Lx and Ly. So which means that in the small, this little tetrahedra that I've drawn, they're not tetrahedra, they're fuzzy tetrahedra. In the same sense in which an electron is a fuzzy rotating stone. So the geometry, it's not correctly pictured like many little tetrahedra at Planck scale with a nice clean Euclidean geometry. The geometry is quantum in the sense that if you look down, these quanta of space are fuzzy. You cannot measure to complete its own geometry. So the quantum aspects of the geometry, are first that the discreteness that come from the fact that the eigenvalue of area and volume are discrete, And second, fuzziness. That's come from the fact that all the variables describing the geometry of these elementary things don't commute with one another. Therefore, you have always fuzziness in the small. There is a third aspect, which is implicit here. If you want, the possible states of geometry are arbitrary linear combination of that. This is a Hilbert space, so it's a linear space. So this standard linearity of quantum mechanics. A single tetrahedron can have a geometry which is a linear combination of this and something else. Standard thing. I mean, a particle can go through holes at the same time of a double slit experiment. Right? Why? Because position is a quantum particle, so the position can be spread. Geometry can be spread. So you can have some geometry, it's a linear combination of geometry. All this is cleanly described by this Hilbert space and these algebra operators. So you have a clean mathematical theory that describes this fuzzy quantum geometry in the small. Okay? Yes?
What about measurements? We can imagine, for instance, for the electron Schleicher to measure the speed, or we can imagine a spectrograph to measure the energy of some wave. What would be the apparatus that would project down state function, a superposition of all those eigenstates to just one with a fuzzy tetrahedron?
Good. Well, if we think about measurement, we measure one variable at a time. So if we may think of having something, anything that determines some amount of space-time. We'll get to space-time in a moment. Let's think about space. And we want to measure its volume, or we want to measure its area, or we want to measure its whatever. So imagine you have some matter, for instance, matter spread in some region, and you want to know how big is this region. Okay. Let's think about area. Area is the so this is a matter, and let's say I want to look at the area of this thing projected from. Okay, so how do I do scattering? I throw particles and see how they scatter. The total scattering amplitude has a dimension of an area. Right, sigma square. How is it called? Sorry.
Cross-section.
Cross-section. The total cross-section has a dimension of an area. In fact, is the area, if you throw things, is the area that is seen by. So the theory says, do any scattering experiment you want, do it super accurately, and you measure the total cross-section, which is in centimeters square. And you will never find anything smaller than 10 to the minus 66 centimeters square, which is a solid prediction, which I can make comfortably, knowing that nobody's going to check it for a while, right? Because we are very far away from a Planck scale. But that's an ideal measurement in which you measure an area. And so it's like angular momentum, right? When you do angular momentum theory, you're computing the eigenvalue for angular momentum of what? Of anything. Anything that has angular momentum has a minimal angular momentum of h bar half. Forgot. So here, anything which determines some region, it cannot determine a region smaller than this amount. And more than that, if I could measure very precisely the total cross-section, it can only be one of these numbers that I have erased. So it can only have this spectrum. Of course, the hope is not to get a check of the theory directly from this measurement, but from something indirectly coming out of that. Good. So, as I said, if we have a graph, a spin network state, one of these spin network states, it can be described by a graph with these quantum numbers. And the J sit on the link, and the Vk sits on the node. Vn sits on the node. So this is a spin network state. And a graph labeled with this number is called a spin network. So a spin network is a graph colored, labeled, with spins on the link and invariant intertwiners on the node, which can be chosen as eigenvalue of the volume. The basis of the eigenvalue of the volume is a natural basis because it diagonalizes some good macroscopic observable. Is not the easy basis to work with because to compute it's hard. The easy basis to work is this one, in which the intertwiner you choose is just two trivalent intertwiner, which you find in Mathematica by writing J1, J2, K, and M1, M2, M, and contracting them. So this basis here, it's convenient for calculations. Is not unique in the sense that if you have a four-valent intertwiner, you can split it this way, you can split it this way, or you can split it this way. So you can pair this with this, with this. But there is a simple relation between this. This is a linear combination with some coefficients, and say this L, and the linear coefficients here. This is standard. SU2 representation theory is called 6J symbol. KL, and here J1, J2, J4, J1, J2, J3, J4, which are written in Mathematica as Wigner 6J symbols. They are quantities which depend on six numbers that can be constructed out of three-dimensional intertwiners, which allow you to do the change of basis from the basis where you use an intermediate representation pairing this or pairing differently. This has a physical, geometrical meaning which is very transparent because, look, remember the dihedral angle here. The dihedral angle is what? Is the scalar product of this and this divided by the area. And if you think what is going on here, this object here is an eigenstate of the operator L acting here, scalar product with L acting here. So this K is actually the quantum number associated with the dihedral angle. So you can write states where what you have diagonal is the four faces and one dihedral angle. And then it's completely spread on the other dihedral angle, but you know how to change basis from one to the other. and this other basis, you have the other dihedral angle, which is sharp, and this is a linear combination of the other. So some time ago, I sort of said, wait a minute. I mean, why can't we just write a state which is sort of not too spread in either of them, the most classical thing we can, right? You can write wave packets in which you have x and p, which are both minimally spread. You cannot, for a particle, have x sharp and p sharp, because if you have x sharp, p is completely spread. If you have p sharp, x is completely spread. But you can write a wave packet where x and p are both minimally spread. For harmonic oscillator, for instance, they are very well known. They're the coherent states. Can we write coherent states here? So I tried by hand at longs to write these things by taking linear combination of that, and then Simone Speziale and Terra Levin did this infinitely better, because in fact there is already a theory of coherent states on SU2, which was developed by mathematicians. So there's a big chapter of, there's a big amount of work, Simone has contributed enormously to that, of coherent states that you can, so coherent state, a linear combination of these things here, which represent a classical geometry at best as possible. And there is an independent way of constructing coherent state, which was developed in Germany by Thomas Tiemann, its friends, and so on. There's a big development of a field to write coherent states. So you take a classical geometry, you discretize it. So now you have all 6 quantities you want, and then you can write states that are minimally possibly spread, but all quantities have the expectation value you want. I'm not going into that now. These are described in the second book in detail. I just want to tell you that out of this Hilbert space, you can write coherent states, which are semi-classical states, wave packets of geometry, which are very useful then for application when you want to a quantum state that describe a classical configuration. You do that. Intuitively, the way I think about this is that this is not a sharp geometry, so this is a sort of blob. This is a blob. This is another blob. This is another blob. And these are sort of minimal elements of geometry. So space-time, not in the sense of relational space-time, not in the sense of Aristotle and Descartes, in the sense of Newton. This thing on which we live is not a continuous thing. It's a quantum thing made by quanta, which have all the standard property of quantum stuff. Namely, they can be in superposition, they have discreteness, and they are minimal blobby things, quanta of space or chunks of space, which on which, of course, the rest of matter lives. The electron can be here, can be here, can be here, and so on and so forth. So the adjacency between these things is exactly what the links describe. So this quantum space is next to this quantum space here. This quantum space is next to this one is not next to this one. So the link describes the quantum numbers describe how big they are in the sense of geometry. So the gravitational field is a thing that we usually call dimension of a region of space, but is not continuous, is not fixed, is discrete, is fuzzy, and it can be in different superpositions. So this is quantum geometry. Questions? That's the picture of quantum space-time of loop quantum gravity. Yes?
So a particle will live at like just one particular node?
Right. Yes. A quantum particle could be more than one because it's spread, but it's the position for a particle is the particle being in one of these nodes. Yes. So, in that sense, in the weak relational sense of that I talked the second lecture, this is space. Okay, it defines spatial relations, adjacency relation. If you want to say where, you can say I'm in Marseille, or you can say, oh, I'm this on this quanta. I'm very small, and I'm sitting on this quantum of space, which happen to have these quantum numbers, and is next to the other one. Okay. So this would close the sort of this construction of the kinematics. We have to go to the dynamics. This will happen tomorrow. Now we start. You look tired, so I'll stop here. Tomorrow we'll go back to a conceptual approach. So no more equations for a while, and talk about time. Okay, and the discussion time will be quite similar to space with a lot more pieces, ingredients of it, because time is quantum gravity is confusing. I'll try to clarify, like I did for space, for then building what is time. Here there is no time, right? These are just things sitting there. Where is time? Okay, so see you tomorrow.